Sleeping the whole. I watched that.
Oh yeah. You know how Russell goes.
I only had a highlighter and a pen to work with.
The average is like 30.
I know. I don't want to download it.
It is what it is.
Downloading cannabis is illegal.
You wouldn't download cannabis, would you?
I mean, I answered.
Sample tests. Yes.
Okay. We are going to go over exam 2 from last semester. Exam 2 from last semester should be somewhat similar to your exam next week. Topics and such that. Yes?
Historically, has he thrown weird curveball questions on exams too?
Last semester, yes. I doubt this semester. He'll probably just change up the wording.
Have you seen the exam yet?
No, he hasn't made it. No. But I will see it before the exam, so. Don't ask me what's on it, though. Okay. Before we start, yes?
Is this exam like on campus?
Yes. The one that's on Canvas. Before I start, I'm gonna just go over a few things. Most of y'all know this already, but whenever we put in our calculator, let's say tan, y'all don't have to write this down, it's just tan 5 pi. Which mode do we need to have our calculator in?
Radians.
Radians. What if we have something like that? Can we just put that into the calculator? No. So this is probably some of the mistakes y'all were making on exam 1 and your homework. Somehow y'all were making mistakes on your homework. Yes. Also, chapter 1. Everyone's gonna need to have that on your cheat sheet. Yes.
For what table is that?
Table 1-5.
Yeah, we need that in our assignment.
Yes. It's especially since we're dealing with waves now. And especially waves dealing in the complex plane and then going back into time. There's less of it this semester, but we see where you end up having where it's cos omega t plus your phase, where this phase, y'all just put your, whenever you have your exponent, you have something with j, y'all just put this here. Don't do that. You don't bring over the j. Leave the j in complex. This is time, no j's. If your answer has a j, you did something wrong. So just, yeah. Either way, moving forward. So this, we are given an antenna that has an unknown impedance that is in a transmission line of 50 ohms.
Zoom in the camera just a little. Never mind.
Okay. Okay, so we are given so this, that length is 0.25825 wavelengths. This length is 0.453599 wavelengths. We are finding ZA. Hint, maybe we are given a short stub here. Hint, maybe you'll see an open stub. So maybe try solving this one open-wise. Could be good practice. Maybe. Just maybe. Either way. So we know from this is where Twitch is probably gonna hate it. Either way, through some math, we know that L short is equal to wavelength times 2 pi, the inverse tan of ZS over J Z naught. Where RZS is this. That's our ZS.
So GA was.
It's a
Oh,
yes.
that's an S.
Yes.
Sorry, I thought
Wait until he gets his
See, I
sixes.
see all over.
There's no sixes in any of these problems.
Wait until he gets to his sixes.
There's no sixes. Either way, we're given this as being L short, but you may come into some problems. If you put this in into your calculator, you will have a problem. Yeah. Your calculator is not going to know what to do with it, given this value of L short. Now, we know that these happened. Where's this thing on here? Where did I put it? How much do I add? How much am I gonna add? And now I'm lost. Where'd it go? Where'd you go? Where'd you go? I found it. I have found it. I have found it. I have found it. Okay. Normally, when we're finding single stub matching, we start at the load and going forward to find our stub. And during that, sometimes when we have to find the shortest one, and we can't have negative lengths, we add a half a wavelength to our value, to our lengths. So this is what happened with this one. This, in the finding of the value, ended up having a negative for the first one. So we add the half to make it positive, to make it a real length.
half a lambda.
Yes. So in this, we would be subtracting half a lambda. We would be ending up getting,
How would we know that though?
you end up with an error.
When I solved it, I didn't end up with an error because you're plug in L short.
Yeah.
Divide over lambda over 2 pi, and then tangent of both sides, and then multiply by jz.
You only get an error when you see something.
Only if you do the negative.
I was just kind of freaking out because there was a variable on both sides. Or, like, when you did find out lambda.
Yes. It's when you do seesaw.
Yeah, because I just solved it by step in my calculator instead of seesaw.
This happened to me one of
Yeah.
when I let you see something and I was super
Sometimes it's because of tan. When you use tan, it messes up. By the way, you end up with the same answer. That's a point.
You add leg over 2 to the whole, right?
Yes. Yeah.
Are we subtracting one over two?
Yes.
Okay. And does this allow C-cell to work?
Hmm.
While we're doing
What happened?
it? I mean, if you don't have to subtract n over 2, as long as you can just do it manually in your calculator by one.
To make it go faster.
So just to do C-cell.
Yes.
Do we know why?
Tan. Because of tangent.
Just
Tangent.
it likes negative value.
Yes.
Wait, once.
It's only undefined.
It's undefined.
Yeah. So think of it that way. Undefined.
Same
Yeah.
answer.
Yeah.
So
So you
it's
can only
just
have
a
four guys, right?
Yeah,
So 2 of them are gonna give
You
you
ended
negative
up with-
values.
-15?
Yeah.
Yeah.
Do we know what lambda is? I mean, how would we subtract?
Well, you just manipulated it out correctly,
Yeah.
but like you're saying, we can just add like you would use C-cell.
Mm-hmm.
Wait, are you adding or subtracting?
Subtracting.
Sorry.
You'll get a negative. We should end up with ZS being -15. Well, I'm leaving it there.
What's the value of L short once you subtract n over 2 again?
What happened?
What's the value of L short once you subtract n over 2?
-0.04. It's cut off. This one.
Is that 6?
Yes. Oh, there's 6.
Make sure.
Damn it, guys.
Either way, since we know it's matched, we know that our gamma is 0. At this location. Oh, that's a.
See it.
Well, any location before that too, since it's matched. Oh, I need another color. Hope this one works. We'll go here. It's not working. It's so we got Zn at this place, this value.
Is it the same place?
Yes, at the same location, the same nodes. So in that case, we know ZS and Zn are in parallel with each other. So for our gamma to be equal to 0, we need ZL to be the same value as Z naught. So we need that equal to be 50. In our case, ZL is going to be the parallel impedance of our ZS and ZN. So we know that has to be true.
Say ZL is ZS parallel with ZN.
Mhm.
Sorry for repeating.
This,
Yeah.
this, this ZL. ZL in this function, this, in this statement, at this current point.
And also confirming Zn is the condensing of Za.
Yes. From there, our only unknown is ZS. So one thing you could probably say before into this one is saying that Zn is the input impedance for Za at this location. Then you can say Zs is in parallel with Zn, and we get this equation. Because there's some missing things in between for Twacha. One thing he could probably also say is going to say you can add the admittances. Yes?
Yes.
Too many letters in between. So with that, we know that ZS plus YN, or that. That is also true.
Is that a 50 with an upside down cross?
Yes. It's a 50. 1 over 50.
Oh.
You're getting murdered.
Oh well.
Stop trying to insult yourself.
It is what it is. Anyway, we know our ZS, so the only thing we have to find out is our ZN. We could just take the inverse of it and get your YS. Same thing. We end up with ZN being that is a 6, by the way. So that's our Zn. This is the easy one. Almost done. From here, we're going to need our beta, which we know is 2 pi over lambda. And our length that we will be using for our Zn equation will be 0.258251 wavelengths. Now where's our lovely equation? I can never seem to remember. I hope it's recording. Nope. Nope. No. Okay. Where's this going? Okay. We all know that equation. Y'all have your different versions of it. Yes.
That value that you had for length right there was like 0.258. That was distance in the problem.
Yes, it's given.
But it says length in the problem says distance. It's like D.
Yes.
That is okay.
Depends on how you look at it, but no. It's the distance between our matched stub from our load. That's what that distance is.
And then towards the end, you use the L being the length
Yeah.
of the stub.
So usually instead of D, you just have L though, just because.
Yeah. I see why he used L and D, just so it wouldn't be the same thing.
L1 and L2.
That too. Yeah,
Either way.
could do that too. The only unknown in here is the L, or otherwise known as ZA in this problem, from which you could do some manipulation, which I think Twachu would love for you to find the actual equation of ZL in terms of this. He would love that. By the way, you end up getting ZA being 73 minus 200. Yes. So tiny. Very simple. And like I said, he could change up the problem where you'll be given an open stub. And the only thing that changes is the very beginning, your value that you end up being, the value for ZS is going to be different. Where that's your L open, the length of the open stub.
That's the only difference between the open and short.
Yes. The book does go over it a little bit more. Where, yeah.
So the gamma 0 at CS, is it 0 for the rest of line 2 behind that, to the left of it?
Yes, from here to there. It's 0. Because that means all your power going in is not being reflected back. It's going through the line.
You move it up.
By the way, that was the first one. Oh, not that one.
I'm sorry for asking again. What did you say the difference was between the open and the short was?
It's the way that it's getting the way that the way that the line looks at it as an impedance is different, and the book does go over a little bit more in chapter 2 at the end, because you can always find the actual impedance here of the open or the short, and then bring it in to find the input impedance there, which would be your ZS. And this is the manipulation of this one, where you end up finding L, given ZL being either an open or a short. Yes.
So the difference between the L open and L short is that they flip the terms in the inverse tangent.
Yes. Yes. Go with that. Next one. So we're given a wire that is in a square with internal resistance of 7 ohms on the XY plane. Free space. The area is 4 meters squared. With the center being at the orange origin, not the orange origin. Oh, that's horrible. That's horrible. That's horrible. That's horrible. Oh, that's horrible. That's...
You may try again.
I'm gonna try again. I should have started with the square. Why am I using purple? Poor purple. Okay, by the way. There are a couple examples of this one, past exams for this type of question as well. You may change up the shape. That's possible, you know. Could be given a circle.
Give us a star on this one.
Why?
No, it has to be 3 questions, so no star. Maybe rectangle. Rectangle could be.
Oh, that's that would I don't.
Rectangle could be it. Either way. We know that each length is 2 because we have to get 4 meters squared. And that's at the origin. So we know this is 1. That's 1. That's 1. They're all 1s. The intersections are a 1. Oh, wait, that's should be 3 zeros. We got it. It's okay. So we're given flux density. And we gotta find the current through the loop. The equation we'll be using V equals IR. Now, our only unknown is VMF. The equation for VMF, that's yeah. Let's solve this step by step. Let's solve the integral first. Since we know since we are given a surface, we're gonna go look at our lovely tables. Unless you have it memorized, of our surface and the way that we're going to be integrating this. We are going to take it. Yes.
Tables. And another useful table in the book to consult.
Yes. Yes. Table 3-1 gives you a good overview. It's 3-1. Here are the surface areas. So if you give it in the XY plane, XYZ plane, you can use all of these. Cylindrical or spherical can be cylindrical if maybe you give it a circle. You could do that. It's a bit difficult because you gotta know the area of a circle. It's pretty simple. But you know, during the exam, you forget equations. So in our case, our D of S is gonna be that one. Good way of knowing which one to use is understanding we're taking the dot of it. We have a Z. So we'll have a Z. Just pick the one, the same one. Some other math up behind it, but other than that, our integral turns into, after taking the dot, now what are our bounds?
-1 into 1 and -1 on 1.
Yes.
This should just give us our area, right?
Yes. For the surface. This is when your Math 3319 skills are gonna. Once we take the integral, We'll end up with that. And then we just take the derivative with respect to time with a negative. So the negative from the sign cancels out. How many zeros? 4 zeros. 1, 2, 3, 4.
Ouch.
Where's the negative cancel out again?
When you take the derivative with respect to time,
Oh,
cos. Yes. Okay. Now we go all the way back up. We know VMF and we know our R given as 7. 7. All you do is just divide or just leave it. You could just leave it as 80,000 divided by 7. But if you want the number,
The negative DDT is supposed to be there, right?
yes, we just only did the integral.
Oh.
If there were like two components given in B, like for example, you have the y unit vector and something plus z unit vector plus something, then for ds we take both the z and y, right?
Yes, you split up the integral.
And then when you do the dot product, y dot z becomes 0. It cancels out, right?
You're gonna do twice. You do the surface for each component. For the z and the other. So if it's z and y, you do the component for the z and the y.
Yeah, but at once, right?
Yeah. No, separately. Because it's x plus the y. So when you take the integral, you can split it up. Correct? It should distribute. Yeah, it's gonna distribute. Where's the? Yeah. So it's
It's double head on the, or double head on the bottom.
yeah. You could do that as well. So it ends up being distributed.
If the surface is still in the z direction, then it's going to be 0 because it's not
So yes. So you would only be using the one that's in that direction.
Directions and bounds are tricky, so that's why we take.
So for this one, since it's in the z direction, okay, let's say it's in the y direction. Y. Then our d of s would be the y, so we'd only be keeping the y. Yeah. Oh, one more question. I'm trying to figure that out. Part B, the more simpler one.
More simple. Like all that.
Does anyone have any ideas about B?
Take the square and we throw it really fast. We get extra. That's what you call it.
A whole page for this?
You want
No.
this one? Yeah, 100 feet a second.
How are we gonna? Okay, that would be.
Pretty big.
Anyone got any ideas on B?
Isn't there EMF transformer for the EMF motion? We have to sum this up.
There is a long way you could do it.
We can't use the simplified version of Ampere's law, whichever one the maximum equation. Yeah. There's one that made an assumption that it's the transformer law.
That's not this one though, right? Because that's on the partial version, right? Where you make the assumption that it's stationary. So we're already going with the general case, right?
Okay. So it all depends on the magnetic flux that we're given. Where was this? How do I describe this? So this magnetic flux is not in terms of time. So when we take the derivative based on time, yes, there's nothing to take the derivative of. So for this one, it's arbitrary.
So how do we draw that conclusion? Like, we're right down.
I would say. Start the same as well. And then here would be when you would say it's equal to 0.
If our magnetic flux density was a function of time, how do we go about solving that?
That one. I love this. I love this. This is what, oh, I see now. I see now. Where was that? Where was that? You would be taking the cross of them, where your u is your velocity.
That gives us electric flux density, don't it?
Yes. Yes, that's that one. Yes, that's the magnetic one. So Q would be I'll come back to that one.
So really quickly, just so I can have this, if that magnetic flux there was a function of time, then it would be the exact same as the first part, right? Just use the DEMF to go through that process.
The velocity is going to change it, and that's what he was asking about. I'll come into that one.
Take the cross product of the velocity and the flux density. You do it before you integrate.
It's the thing is with this one's going to give you the magnetic one, and in the book, the EMF is equal to this one was. This is technically the transformer one. Yes.
It should just give us current. Because it's velocity across the field gives you your current number.
Yes, it should be the current.
Aren't these EMAG equations the same? The only difference is that if it's like a transformer one, you can move the derivative on the inside.
Yeah.
As a partial. So,
It's just changed
so
the way
for
it's
B,
written.
if the density was with respect to time, like cosine 10t,
Mm-hmm.
when would you take the cross product of the velocity that the loop is moving at? You cross them inside the surface interval?
It turns into a contour integral. That's the thing. There's a problem about this. Isn't there a problem on this, the homework? We'll come back to it.
I think what it is,
You
since
speak-
U cross B gives you current, you would find the EMF transformer divided by R and then add the two together. That should give you total current.
This is a different, completely different. So with this one, you would use the MENAG one and then you would divide by the resistance given, which is 7. Yes, it's U cross B gives you 0 in this problem. When you cross X and Z, it gives you a 0, and that's where you get a 0 in this one.
I think
That's
it's
what it was
U cross
too.
B gives you Y, but GL is in the XY coordinate system, so the Y component is well.
There's something cancels out in this one.
That's not right.
Just cross products here.
X crossed with Z gives you Y, and Y dot with the Z gives you 0. That's what the 0 comes from.
DL is
Not DL. DL is something else, correct?
So it's not 0 because
No,
the flux density is not with certain time?
it was coming to me. I'll come back to this one. I'll come back to this one.
Totally get some type of induced current and that would
It's been a summer since I've done this one. We'll come back to it. I'll post the thing about it on Canvas. Solving it if it's time and if it's not time.
Very small.
Okay. We're given the magnetic field intensity. Our permittivity is we have a permittivity. No, it's just not. Okay. First one, we gotta find beta. What's a good equation for beta? Of the numerous ones we may have. Which one?
you said it right.
C divided by X.
It
Yes. Yes, you could use that one. That one should simplify to where is equal to that as well.
What was that be?
Meaning, where UT. Well,
Is that my team?
Where's the T?
the epsilon looks like a T.
It's the epsilon. But it was a T.
Sorry, I was.
Under the square root.
Yeah.
I'm really.
Yeah.
Sorry, go bed. I'm so sorry.
Yeah, I feel bad.
Trying to be right.
You're good to you. Don't listen to these clowns.
That. You got 20 minutes.
You're almost done with this, we promise.
This one's the easier one. Thank God. Thank God this one's the easier one.
It's like, thank God I'm graduating.
That too. Okay, now we gotta find the electric field intensity. Please do not mess up on this. Because we're going into complex.
No problem, says. I'll find a way.
It just makes it a lot easier. So it's at the end of chapter 6, you're given this equation in which we relate the electric field intensity to the magnetic field intensity under certain parameters.
Time varying for, time per month.
Yes. Yes. For this exam, you can use the one in chapter 6. For the next exam, I would probably use the equation that's given in chapter 7. Fine, to relate the electric field to the magnetic field.
Is that the one with the funky looking panda?
Yeah. No. Sorry. This one you can use anytime. That one is under certain cases.
Free space. It's not for.
No, it has to be. It has to be a uniform plane wave. Yes. That's the thing with the equation found in chapter 7. This one makes it, there's a lot more things you have to do, but you know you will be correct. It's that, yeah. That. Nope, that squiggle. That's a squiggle.
Is there a reason you're drawing the line?
Yes, because it's bold. Because it's a vector. The extra line is for boldness for the vector, and the squiggle is for it
So
being
you have to draw
polar. Yes,
an arrow.
complex.
What do you say?
Phaser?
Phaser?
It's complex.
Same thing.
Space.
Complex. Yes,
What does the bold signify?
it's a vector. It's a wave.
Although a strong argument can be made that complex numbers are also vectors. Right.
I mean, you could.
Because the book just. The book is a bold letter with a squiggle. And we can't get boldness
What does he do for that? He does something different.
He does do some.
He does like a cursive for the.
Is that, I thought that was for
No,
time.
no, so.
Doesn't he make it like cursive, right?
Yeah.
He does a cursive to make it bold with the squiggle or something.
No, he does it like in print with the squiggle, but then he does.
I never
cursive.
understood it.
Yeah.
I made my own way of remembering how.
Yeah.
This way I know I have to have a yeah. Either way, very simple. We'll take everything apart. Oh, I'm going to write down the controversial equation. Okay, this is when it gets controversial. People say there's a negative, but the negative distributes inside. Oh, I ran out of room. It still continues. I hope I did not mess it up. Either way. So we have a y. We identify when we take the partial of h of y. And then we find our x in what we're taking the derivative, the partial in respect to. So we have an x. So on the bottom, we have 2. This one's in respect to z, so we can't do nothing with that one. This one's the x. Bingo. So we know it should be z. Then you take the derivative respect of x. And then ij omega, yes, and then our epsilon. We know that, we know that.
I have a question.
Yes.
Isn't the middle term in the y, did you say that you had already distributed the middle one in the y for del cross h, or?
The negative, you're talking about the negative?
Yeah.
Yes.
Yeah.
Here, right?
Yeah, I'm just not, they got flipped, right?
Yes.
Okay, sorry.
So,
Just for
This is
clarity.
where,
so it should be, normally it would be like a negative y, and then on the inside there would be a plus sign.
yes, the one, okay. When you did this in calculus,
Yeah.
there was a negative here.
Yeah.
But in this book, the negative gets distributed through.
Right.
Which makes a lot of sense, you know. Might as well.
There's nothing wrong with that.
Yeah.
There's nothing in math that says you can't do that. So why did you draw an arrow on that X term? The arrow above this one, yeah, why'd you draw this arrow again?
Okay, so this is basically just trying to find, instead of doing all of this, you just find which one you need etching to do.
Oh.
So we look at the top.
So we can ignore the other terms, right?
Yeah.
Okay. I agree.
On the y term, shouldn't one of those not be h?
Oh, dang it.
Second one should be.
Is that it?
Because you get 2 terms.
Yes.
You should get a z you back there in a while.
What?
You get a Z component in Y, so let's take the cross.
Why? Por qué?
Okay. So we're looking at x plus partial z.
I meant. Yeah, I think like
I am so sorry to interrupt, but in the Z term,
Yeah.
that's supposed to be a HY that HZ in the basis term.
Yes. HY, HZ in terms of X and Y.
Should we HX? Yeah, because I'm so sorry.
Let's find it in the book.
I mean, you were right, it's controversial.
It is. I know it's at the end of the book. DZ. Imagine this as an H. The B as an H. Where's this? Okay. Z, Y, H, I mean, Y, Z, X, Z, Z, X, Y, X. Dang it. I wrote it down wrong. I just didn't like the X's. That's what it was.
Nobody does.
Hey, I don't like my exes either.
Oh, that. Either way. That's A and B. Now we gotta find the surface.
Like, what was A? What part was A?
Beta. Part B was finding the time, the electric field. And then our last one is finding the current density. This is Pacha was he was on something last semester when he asked for this.
This is terrible.
It's what happened?
Oh, did I mention you divided by J negative X1? When did you do that?
So you have a 3. The J is cancel. So it's beta over this. So it's basically this divided by this one again. So it's 41 divided by 4 epsilon naught.
How do you find current density?
So current density in the book is a one line under some random little paragraph, because the end of chapter 6 deals with current. It never really deals with density, and it only references density for one little line in the whole chapter. So it was pretty for him to do this. That. Or you know that is that. Yes. Hit. You may need those again.
Shit.
One second.
What's the current density that's like sigma J or sigma E or something like that? To that?
Are you thinking about the one in chapter
It's in here. So if you want to know where this is talked about in the book, it's page 297, where it talks about displacement currents in the current, and then where it, just one little line, talks about displacement current density. So that's where it's in the book. 297. We take the derivative with respect to time of that. Gives us
Is that partial derivative or?
got a z over there. It's just a derivative. And then basically all that's left is this epsilon. You multiply it to this, where we know epsilon in our case is 4 epsilon naught. So our ultimate answer is that. Oh, there's a whole problem about it. That was exam 2.
Is exam 3 better or worse? In your experience.
It's more waves. So, and he may do wave guides. So it could be either.
Is it easier or harder generally? Do you have a better grasp on it around test 3?
It builds on this last question. So if you really enjoyed this,
It's not awful, let's say. First one can be kind of awful. First question.
yeah, it's a little bit easier. The exam 3 is usually 2 questions. So
Did they offer extra credit on exam 3 for y'all last year?
right, it was that. No, it was 2 questions.
Well, they were both 60%.
Yes. Out of 100, yes. He takes it out
Doesn't add
of
up.
takes it out of 100.
Also, There's more on 611 on, or like that.
Yeah,
More than one.
yeah, there's a whole problem about it. Yeah, I saw it. But the equation when it's given is one little line.